if we couple anything up, that will give the audio just fine. All right, so any questions going on for this? Nope? Okay. So what I wanted to do today was just recap the things that we've talked about so far in the class. And the immediate material that we've been discussing has been on relative permeabilities that you might remember. And we talked about the idea that if we want to get material into the subsurface, it goes in quite quickly through this kind of partially saturated column, reaches some equilibrium. If we want to remove it by sucking it out, the rate at which we can take it out is controlled not only by the capillary pressure relationships, which kind of describe the steady distribution of that saturation of the subsurface, but by Darcy's law. And so the way that we deal with Darcy's law in multi-phase flow problems is to be able to look at what we've referred to as relative permeabilities. And this is the key figure in all of this. I think pictorially it does a decent job in terms of how this index of relative permeability here on the left-hand side between 0 and 1 changes as a function of you changing the saturation. So in other words, when it's full of green fluid, the transmission of the green fluid is almost perfect because you'll be 100% saturated with the non-wetting fluid, 0% saturated with the wetting fluid, and therefore the relative permeability curve would give you perfect transmission because the multiplier on permeability would be 100%. But the permeability to the non-wetting to the wetting fluid, rather, in this particular case the water, because it's not connected across the system, in fact this red stuff isn't there at all at this point, there's no permeability to it at all. So multiplying the permeability by the relative permeability of 0 gives you no effect. And that's really all relative permeabilities are. And so what I was going to do was just put everything that we've done so far, put it in some kind of framework, just by kind of summarizing the things that we've talked about. So that's what I plan to do to start. So let's do the, whoops. So we are 2.5, right? So excuse my maybe not so good handwriting. And so this is just a summary. And so if we look at permeability, so the characteristics that we know for now, and so maybe if you can drew these, I was thinking about making you draw these yourselves, like we did last time, but I decided to absolve you of that this week, is if you have room to put two diagrams, one on top of each other, then those will be the same two diagrams maybe we finished off with last time. But I just wanted to summarize kind of everything that, in as short a sense as possible, that we've done over this last maybe three and a bit weeks. So we know that saturation is the percentage that fills the pore space. It's always the saturation of water. I think that in my last stuff that I did on Thursday, that I switched irreducible non-wetting and wetting saturation. So I think that part of our discussion was wrong. It was switched. So if you go back, if you end up going back to those movies, take this one as the gold standard. Right? So you know what these exclusion points are. And what is this exclusion point here? This is the irreducible saturation of something, right? Do you know what? I guess I've given it away. It's irreducible saturation of water, right? This is the amount of, bless you, this is the amount of water that's left in the system even after you've got as much of it out as possible. This is the irreducible saturation of the non-wetting fluid. This is, bless you again, this is relative permeability, and this is either capillary pressure or the J function. It doesn't really matter which one. And we know that these curves look something like, if I can do it well, like this. And geez, everyone's dying. This is 1, this is 0, this is definitely 0, and this is some number. I don't know what it is. It's not 1 or 0. It's a bigger number typically. Well, it's a different number. It's not bounded by a number. And then the capillary pressure versus saturation curves looks like this. This is our drainage curve because you're draining water. This is our imbibition curve because it spontaneously imbibes water. This is, again, saturation of the non-wetting fluid. And of course, it's this length here which defines that. And the other important parameter here is this is the bubbling pressure or the entry pressure. Bubbling, so maybe entry pressure. PC0 equals entry pressure. So that's basically what we've dealt with so far, nothing more than that. So the top one's permeability, which defines flow. The bottom one, for want of, so this is a relative permeability curve. The bottom one, for want of a better term, is a capillary pressure versus saturation curve. And they say two different things about our system. We looked at two different analogs for materials, which were either porous or fractured. And if I'm not sure if you remember the kind of cameos of this, the porous medium looked like this with a whole bunch of different Swiss cheese with pore sizes in it. Each of these had some kind of diameter to it. And we said that the permeability, we derived this last time, one approximation of it is something that is defined as the square of the pore diameter, the porosity of the porous medium, and some multiplier, 96 or 32. We derived that last time. We haven't done this yet, but we'll talk about it today. If you look at a fractured medium, where the characteristics of that fractured medium are a whole bunch of fractures which are separated from each other by some spacing between individual fractures, which we'll call S, and some aperture of the fracture, which we'll call B, then you can actually define the permeability also for this fractured medium in the same way as we had three different values for this. In this particular case, it would be the aperture cubed divided by 12 times the spacing between fractures. So we haven't derived that, but we could do if we wanted to. We know that these relative permeability magnitudes, by definition, are greater than 0 and less than 1. In other words, on this curve here. And what we use it for is we use it to calculate the effective permeability of a phase, and the phase would be water or oil or air, which we call alpha. And the effective permeability is just the relative permeability to that phase, which is a function of saturation, multiplied by the permeability at a saturation of, what do I do? Saturation of alpha, I guess, at 100%. That's all. That's all what effective permeability is. And so what the practical application of that is, if you want to calculate the flow rate, the volumetric flow rate of some phase alpha, you can get it by multiplying a cross-sectional area by an effective permeability times divided by viscosity, multiplied by the density of the fluid, multiplied by gravity, and the head gradient across the system. So we talked last time about this swimming pool effect, and what pressure meant. Even if a swimming pool, the gradient is finite as you go down, but there's no flow in a swimming pool. And so one way you can get around that is using heads to calculate flows. And maybe we'll do an example today to be able to do that. So in other words, if you substitute this parameter in here for this effective permeability, divide by the viscosity of that fluid, whatever that fluid is, density of the fluid, this is rho, gravity, and the gradient, then you can get the volumetric flow rate. And it should be in units of length cubed over time. And so that gives us the ability to calculate volumetric flow rates, which we want to know, right, if you want to calculate how quickly you can suck stuff out of the subsurface. So that's what we talked about in terms of flow rates, permeabilities. The other things that we talked about in terms of relatively permeability curves, also defined in terms of the same diameters of capillaries or the apertures of fractures, was that this entry pressure H sub C0 would be equal to 4 times the interfacial tension divided by the diameter and the unit weight of the fluid, density of the fluid times gravity. If we want to write that as a capillary pressure and entry pressure, PC0, then that is given by, we just multiply by the density of the fluid and gravity, so it's just the same expression, but without this term in here. And if we want to do that for fracture, I guess we also did that for fracture. The entry pressure, if you remember it, was equal to 2 times the interfacial tension divided by the aperture of the fracture, and also the unit weight of the fluid. And so that also gave us a capillary entry pressure of just 2 times interfacial tension divided by aperture. So these are the expressions actually that you're going to use in this assignment too, for example. You may want to use to calculate capacities. And that's it. And that's kind of a summary of everything that we've talked about so far. The other interesting thing that we can do is that clearly these relationships are connected to each other. And they're connected to each other because they're both vary with saturation. These are these kind of no-go areas. This no-go area is here where you can't get all the air out of the system or the napple out of the system. And this no-go area here is where you're left with some water in the system, even though you've invaded it completely with either air or napple. This would be the relative permeability of to which fluid, if you look at this one. No. So it's 100% permeable to a fluid when there's 0 water in it, and so the fluid that is present at 100% is the napple. So this is the non-wetting fluid for this one. So good for taking a stab at it though. And the wetting fluid here, yeah, it's the opposite way around. So that applies. This is imbibition, and we've looked at these curves, and we'll look at them again. So the other interesting thing, okay, I know I'm resorting to my indulgence of derivations, etc. But these are key properties. I mean, I think what potentially makes you a powerful employee to a company is that you can do calculations that allow you to quantify things. So these are my quote-unquote, people laugh at me, my back-of-the-envelope calculation equations. You can do all kinds of things to get a sense of the order of magnitude of behaviors from these and other equations that we'll talk about. But the other thing which links these two together, which I think is fascinating, perhaps it's just me that thinks it's fascinating, is if you take this expression for, and you can do it for fractured rock as well as just for porous medium, if you take the capillary pressure as the entry pressure, which is 4 times the interfacial tension divided by the diameter. So if you like, if we link relative permeabilities, and not relative permeabilities, but permeabilities and capillary pressures. You think that they're related in some way because they both vary with saturation. So what we could do is we could try and link capillary pressure to permeability by realizing that permeability is defined as a function of this conduit size, which also appears here. So if we rewrote this expression, we could write this as what? We could write it as d squared, just by rearranging this, is equal to 96 times permeability over porosity. And we could square root both sides. And we Obviously, this is equal just now to D, and we could throw this expression into here. And so if we do that, we end up with PC0 is equal to 4 times the interfacial tension, and we have square root 96, and we'll have K over N, all square root. And if we wanted to, so we can define permeability now. So, sorry, capillary pressure should be inversely proportional to the square root of permeability. Porosity doesn't vary very much, so we don't care. And it should be directly proportional to interfacial tension. But what we can also do with this, I suppose, is we could rearrange this further just by dividing through both sides by interfacial tension and dividing both sides through by, or multiplying both sides through by porosity over permeability square root, in which case we would end up with something I think that might look similar to you now. And, sorry, that's not an equals. And, oh yeah, I guess it is, which is equal to 4 over 96 square root. So 84 minus, so what's the square root of 96? Is it an integer? No. Sorry? No. What's it close to then? About 10, right? So I can't do it either. So square root of 100 is 10, right? So, and so, isn't that amazing? Don't you think, have you seen this before? Isn't that incredible? Doesn't that explain everything you ever wanted to know about this class? Is that this value is 0.4. So we've seen that before, right? And, oh, it's even fortuitously here, right? I'm guessing that this number here, I can't write on this because it's in a browser, but I'm guessing this number, instead of being 0.3, is actually, well, it's pretty close to, it should be square root 4 over 96, which I guess would be a point, it should be up here, right? But that's basically the idea. And so these things are linked. They're linked because these curves, if you stack them on top of each other, like we've done here, are related via the saturation of the fluid that's in them. This is 100% saturation of water. We're using a very simple model to represent the permeability behavior and the capillary behavior based on single capillaries. And so it's perhaps not surprising that it comes out to be the same. And so that's the kind of linkage between these. And so that's maybe an aside, but that's an important step to make. So the important thing, I think, I don't care if you know this. I care that these, you'll probably end up using these expressions to some degree. So it's important to know that we've talked about them. I think this is quite an important connection because it kind of intrinsically makes the point that capillary pressure and relative permeability behavior are linked through a common variable. And of course, in a porous medium at any particular time, you can only have one saturation of water and the non-wetting fluid at a point, and therefore you have a unique point on this curve, which is just, you know, some location on this curve. So at any particular time in a porous medium, you find yourself on a curve. So depending whether you're on the drainage part or the imbibition part, you'll have a unique capillary pressure present at that location, which is just the difference between the pressures of the two fluids. And you'll have a unique magnitude of the permeability of the non-wetting fluid and the permeability of the wetting fluid in that particular case. And so these parameters allow you then, if you know what the saturation is, you could, or if you knew, for instance, probably the more likely thing is if you know where you are in the vertical point in your section, you could calculate what the capillary pressure is. If you know what the capillary pressure is, you have a chance of knowing what the saturation is through this curve. And if you know what the saturation through this curve is, you also know what the relative permeabilities are. And so you know the rates at which you can pull fluid out of the system. And that's basically the idea. Okay. So anyway, so that's kind of the big picture and how these things are linked together. And so everything that we've talked about should, if it didn't already, should make it some sense. I won't go through this material, but I will kind of explain in overview some features of these relative permeability curves which may or may not be fascinating, but are features nonetheless. And that is that we've seen these curves. We have these kind of exclusion zones off to the side. This is the irreducible saturation of the wetting fluid, I guess, which is marked here. This is the irreducible saturation of the non-wetting fluid. They do have to join up with these points here, but this is a difficult area to make measurements with because you can't really get saturations to change very easily in there without evaporating fluids, typically. But so sometimes these curves are shown with this cutoff, but they do have some values that go there, and so you can either do it by extending the curves like we've done here in the blue, or you could choose some other arrangement. You'll notice also that the relative permeability curves are always between 0 and 1. You'll know that if at any particular, this dashed curve here is just the sum of these two curves. So in other words, at this particular saturation here, this dashed curve is this height plus this height, just added on the top. That's all. And so it just makes the point that the sum of those two curves is always less than 1. You think that since the saturation, as we made the point earlier on, the saturation is really making the case that what physically happens is that it changes the amount of your core, which is saturated by one fluid, and the remaining part of the core is saturated with the other fluid. So it really is just defining two parts of your core in which each of these fluids are individually flowing. So if you have something completely saturating the red part of the core and flowing, and a different fluid saturating the green part of the core and flowing, you might think that the sum of those two flow rates would add up to the same flow rate as if it was saturated all with the one fluid, the red fluid. But what these curves tell you is that that's not the case. If that was the case, then what would happen is that the two of these curves, when you added this curve to this curve, they'd add up to 1. And that's not the case. And so what it is that when you fill it up with the pore structure, it really isn't arranged in that way that half the core is filled with red and half the core is filled with green. It's actually much closer to this kind of sinuous ganglion of fluid that has to flow through some kind of tortuous flow path to get there. And in flowing through this tortuous flow path, it's flowing longer than it would do just from the upstream face to the downstream face. And as a result, it's less efficient. And so it reflects that lack of efficiency by having the sum of those two relative perm terms as being much less than 1, I guess, might be one way to think about it, much less than 1. Okay? In the same way that we talked about capillary pressure curves, that we had not only if we talk about capillary pressure versus saturation curves, and we have both this drainage curve and an imbibition curve, that if you stop changing the capillary pressure at some magnitude and you move here, then you go across these scanning curves and you can rejoin it in the same way. Well, in the same way that it matters whether you're draining water or imbibing water on what it means to the capillary pressure behavior, it makes exactly the same behavior as if you're talking about relative permeability curves. There's not a unique value of relative permeability. If you're at this saturation, it matters whether you're on this curve going up through this point or if you've been up here and come down. So there's hysteresis. And it's hysteresis because it matters whether the rock has been previously wet by that fluid or not. And so you'd expect, perhaps, as a consequence of this behavior, it's perhaps not very surprising that we have these curves that exist as separate curves. And actually, although it's rarely done, you'd also expect to find these kind of scanning curves that you'd get as if you moved between these by changing the saturations in this particular case. You'd move between these by filling up the space between those two curves. And if you have different pore throat distributions, pore size distributions, you'd expect to have different capillary pressure curves that result in the same way. You know, we made the point before, I think it's more straightforward to understand it when you think about capillary pressure versus saturation curves, that, for instance, if you have, sorry, I did that wrong, didn't I? This is saturation. So if you have a curve that looks like this, versus a curve that I can't use different colors, that looks like this, you could say a couple of different things about those porous media, right? What could you tell me about the difference between porous medium A versus porous medium B from that capillary pressure versus saturation curve? Give it a go. Yeah, you can do it.
Does A have a uniform porous?
Yeah, fantastic. Yeah, so you know that once you invade the pore size, you invade the whole thing, so A is uniform. B is less uniform, so that's the one thing between those. What else? So you can say something from the shape of that, that's great. What else can you say from the magnitude of this intercept? Is the biggest pore size in porous medium B larger or smaller than the one in A?
Pore sizes are smaller.
Yeah, that's right. Yeah, you don't put your hand up, just shout. It's fine. Great, fine. So those are two things. And so you'd expect to see exactly that same behavior from this. So in this particular case, so the non-wetting fluid will take the largest pore throat. So I'm thinking in this case that, let's see, you have a higher, I've not really thought about this in any great detail. You have a highest permeability. So here you have a much, you don't have a very sharp gradation in pores because this is relatively uniform. So in other words, if you've changed the or is that the case? So you're changing the saturation in this particular case, but the permeability doesn't change. So in other words, you're not invading much more pore space. So I guess that may be that with a big change in saturation, you don't invade much more pore space. So actually, I don't know what it means in that case. I'll have to think about that. But basically, these mean that you have different distributions of permeabilities, and again, invading the largest pores first. So I'm guessing that this has a large population of large pores because the permeability stays high, even though you're filling up with more and more water as you go across to this right-hand side. And so you have a large population of large pores, I think, in this case. And so the permeability is staying high as a result of that. I don't know what it says about the capillary pressure. Perhaps it doesn't say anything about the absolute size of those pore traces. But I think it says something about the distribution as being more uniform distribution because this is relatively flat, just as in this case the capillary pressure curve was relatively flat, which represented a very uniform pore throat distribution. Okay? All right, so if we come back to this, so the one thing that we invoked when we looked at this relationship between capillary pressure curves and permeability was that we could link them through saturation, and we end up with this curve. To do that, we needed to have some kind of magnitude that linked the pore throat size to the permeability, and then if we did that, then we could link these two things in some way. You could also make the same relationship as this by using both the capillary pressure expression we have for fracture with the permeability expression, which we don't yet have for fracture, but which is this one. So we could do exactly the same as we've already done for that. And I won't go through the derivation because I don't think it's particularly important for us to do that. But if you need some reason for having taken fluid mechanics in your past, we talked about the flow of fluids through a parallel-sided duct, in which case flow through a duct would give you this kind of parabolic velocity profile with the largest velocity in the center, zero velocity at the edges where it's attached to the walls of this. And if you do that, you can get the flow rate that goes through this as a function of either the pressure gradient or the head gradient you apply along the length of this, the aperture, the separation, if you like, between these walls, which we call B, and the kinematic viscosity. What's the kinematic viscosity? It's the dynamic viscosity, which we usually use, divided by density, right here. I always want to use gravity, but it's density. And so we know everything here. So in the same way as we did before, if we know the amount of flow that occurs in one of these fractures, what we could is we could take a whole bunch of these fractures that are separated by some length and sum up their effect to get the total flow, not due to one fracture, which is this case, but due to a whole number of fractures. And the whole number of fractures would be that if the spacing between fractures is S, then the number of fractures we have per meter is 1 over S, right? If you have 0.5 of a meter between fractures, you have 2 fractures per meter. And the way you get there is just by dividing the spacing of 0.25, take its reciprocal. So 1 over 0.5 is equal to 2, so the multiplier is 2. And if you do that and you multiply by the cross-sectional area of this fracture, which is B times the length into the page, then you end up with an expression which we defined already. We said it was 12, but for one fracture, it's equal to, in our terminology, this is, sorry. In our terminology, this is B cubed over, no, let me do that. I could derive it from there because we know, for instance, that hydraulic conductivity divided by density and gravity is equal to permeability divided by viscosity. And so if we wanted to, we could take this value here and create it to a permeability, in which case permeability would be equal to what? Hydraulic conductivity, density, gravity, and viscosity. And so if we take this parameter here, no, I don't want to do that because I'm mucking this up. And if I do that here, we'd end up with G B cubed times viscosity divided by 6 times, we already said that viscosity is mu over rho, and times spacing. Is that going to work out for us? Well, certainly we get rid of these. And I guess we also have to multiply by rho g. So we lose this and we lose this. And miraculously, we have permeability as B cubed over 6s. We said 12s, bless you. And the reason for 6s is because, which is equal to B cubed over 2 times 12s. And the reason for, is that right? Yeah, multiply top and bottom by 2. The reason for that is that now we have the behavior for one set of fractures, which will give us a certain amount of flow. If you add another set of fractures, which are here and here, which are also separated by the same spacing, then that will give you an equivalent amount of flow due to this. So 1 over 12 gives you 1, 2 over 12 gives you the effect for 2 of these, and this is the effect for 2 of these. And so it doesn't really matter. It may seem kind of arbitrary as to whether you use a 6 or a 12 as the numerator or denominator, but the reality is that, you know, the unknowns, the uncertainty in most hydrologic systems is so far greater than that, where you have permeabilities spanning maybe 6 or 10 or a dozen orders of magnitude, that a change by a factor of 2 makes no difference whatsoever. So I know you might not be used to this, where you're expected to get answers to 2 decimal places for your assignments, but in reality, when you're doing calculations, this factor of 2 doesn't make any difference. And so you can imagine that if you're looking at flow in fractures, you can use the same idea of relative permeabilities to be able to look at the behavior in fractures, where you have a relative permeability of the wetting fluid, which is red here, and a relative permeability to the non-wetting fluid. Instead of a whole bunch of capillaries, which are capillary tubes which are joined in some way, you just have a whole series of fractures, or a fracture which has a rough surface, which in this case, this would be the surface of the fracture, which is changing in elevation as you go across it. This is the top of the fracture. This is the bottom of the fracture. And so you could think about a parallel plate which is wide here, go downstream, it widens up into a bigger one, shortens down into a smaller one, and that's what this is kind of representing. And so this again gives the same relationship between relative permeability and saturations that we had before. Okay? And so if you think about, if you wanted to, you could do exactly the same as we did before. You could represent the permeability in terms of an aperture, which would be what? B cubed is equal to permeability, which you can measure, times 12 times the spacing. You cube root both sides, and you have an aperture. And actually, you know, that's the one thing that you'll end up using in assignments, is that typically one thing you can never do, you can't go into a fractured rock, you can't go down a well bore with a borehole camera and look at the fractures in the side of that well bore and say, well, I think the aperture of that is about a millimeter, or a tenth of a millimeter, or a hundredth of a millimeter. But clearly the apertures of the fractures or the pore diameters are incredibly important scaling properties for us, because they relate the capillary behavior and the permeability behavior. So what you could do is you could do a pump test on something. You could measure the permeability in that pump test. And if you know from looking at outcrops or how widely spaced the fractures are in your borehole, which you can see really easily, so they're a foot apart or a meter apart between fractures, if you know these two values, then you have a rough idea of the aperture to some degree. If you know what the aperture is to some degree, you have a chance of being able to reconstruct this capillary pressure versus saturation curve, either from this expression or directly from knowledge of the permeability that you started off in the first place. And so you can make these linkages so that at least the parameters you have are consistent between your choices, because they are related in some way through saturation. Okay. And I know I'm belaboring that point. But anyway, it's important stuff to get. And this is the derivation that we went before. Okay? All right. So we've talked in maybe excruciating detail about linking these in terms of their properties and how they behave with saturation and what that physically means in terms of saturation. And that's probably about as far as we need to go in terms of applying these models to multiphase flow in this class. But the other thing that we need to be able to solve any realistic problems with this is that basically what Darcy's law allows us to do, and maybe I should do that, is that Darcy's law allows us to basically do this. It allows us to take a core, and, well, actually perhaps now is the time to do the example. Right? And you take a core, and maybe you have, because you'll do, I think assignment number 4 for you is exactly to do this, and say that if you had piezometers on this core, that you'd have some fluid levels which are present in this to some height, H1 here and H2 here. And so the question is, if this component is filled with fluids with, say, a saturation of water equals 70%, and say a saturation of oil which equals 30%. And I was to ask you how much would be the flow rate of each of these components out of this sample if we put a pressure gradient across it or did an experiment with it, then how'd you calculate that? So it's straightforward, right? We've kind of covered the ground for it already. We know that the permeability is equal to this total cross-sectional area, which is this dashed line here, the total area. Maybe you should call it A sub T for the total cross-sectional area. So it's pi times the diameter of our core squared. So this is a core. It's not a capillary, it's a core, which contains both of these fluids. We know that the relative permeability, which is a function of the saturation of water, multiplied by the absolute permeability of the core, divided by the viscosity, and multiplied by the head gradient, will give us that amount. We know that the flow rate of whatever phases we're interested in, so this is alpha equals 1, let's say, alpha equals 2. So just by definition, the wetting phase is 1. We've just chosen that. And we know that the permeability of this core is, choose a number. A sand might be Berea, which is a common reservoir. A sand might be 1 millidarcy. So 1 millidarcy is equal to 10 to the minus 3 meters squared in terms of units. So permeability, not hydraulic conductivity. Hydraulic conductivity is velocity, length over time, meters per second, centimeters a second. Permeability is length squared. And we said that permeability in some way is a proxy for the square of the pore diameter. Right? We made that point. And so how would we solve that problem? Well, you need a relative permeability curve. And that relative permeability curve would look like this. This is a saturation of water. This is 0. This is 100%. So the water saturation of 70% is going to be here. This is 1. This is 0. This is going to be the relative permeability to the wetting phase, right? Because it's 100% saturated, it's 100% permeability. And so I don't know what that is. Maybe that is equal to 0.6. You choose your number. This is the relative perm of the non-wetting fluid. And maybe that's equal to, it's less than 0.1, but I like nice round numbers. So it's 0.1. And so if you want to get the volumetric flow of water, it's going to be equal to whatever this area is. It'll be the same in either case. So this is, I don't want to use lowercase d, so this is, you know this, AT is equal to pi uppercase d squared upon 4. The relative permeability for water is 0.6. The absolute permeability is 10 to the minus 3 meters squared. It's divided by the viscosity of water, which is of the order 10 to the minus 3 Pascal seconds, as I recall. And the head gradient. And the head gradient is just going to be whatever the height of H1 minus H2 is, divided by the length of your sample. That's it. And I'm not going to do the calculation. The one for the non-wetting phase should be the same area. It should be 0.1. Should be the same absolute permeability, and it should be the same. It should now be the viscosity of the other fluid, which would be, don't know, of the non-wetting fluid. And again, it should be the difference between these pressures, kind of. Not absolutely true, but good enough for this class. And what's missing? The units of this aren't going to work out, right? Because it's not multiplied by the density of the fluid times G, density of water times G, and this could be the density of the non-wetting fluid times G. So I say this isn't completely right is because we've chosen to use heads instead of capillary pressures. And there's a problem when you use capillary pressures is that we know by definition, so a philosophical problem, right? So we know that capillary pressure by definition is equal to the non-wetting fluid minus the wetting fluid, and is equal to what we've said is the head difference multiplied by the unit weight of a fluid, or the capillary difference. So that's fine. So you have a capillary difference that you can use, but of course here you have two potential fluids that you could use the unit weight of, and they're not necessarily the same. And so when we do this simplification for permeability calculations using heads, then intrinsically we've changed a little bit because we're not sure what unit weight that we should use in these particular cases because we've messed it around a little bit. But For the purpose of this class, it's actually okay, I think, you'll find it easier to use heads, even though strictly speaking, there's a certain error that's attached to that. And if you understand that error, great. If you don't, then that's okay as well. And so you'd have two numbers that come out of this, and it would probably tell you that the amount of fluid that came out of the water was much more by a factor of a few, right, so 6 times in terms of the relative permeability than this case. Of course, you don't know what this is in that particular case, and it matters with these densities as well, which might vary by, if this is a DNAPL, maybe this is 1,500 kilograms per cubic meter, and maybe this is 1,000. So maybe by 1.5 to 1. But the biggest change would be in terms of these rel perms. Of course, the other question is, what would be the flow that came out of these if the saturation of this system, what happens if the saturation, instead of being 70%, was 90% and 10%? Philosophically, how might that change our calculation? So do you think, let me be direct, do you think there'd be a flow of the non-wetting fluid? Right? This would suggest that it is, right? If I draw these curves like this. So this is the flow of the wetting fluid, water. This, instead of being 0.6, it would be 0.7. This, instead of being 0.1, would be 0.05. That's okay. But what we've ignored, maybe, is that we haven't drawn our figure like this. And so if we drew our curves actually to replicate the fact that this does this, but this is already bottomed out, then indeed the permeability of our other phase would be, instead of 0.7 and 0.05, this one would be nothing, right? And so there'd be no flow in this particular case. And that makes sense because of the equations, but more importantly, it kind of makes sense because of this picture here, right? And that is that in this case, the water is the red fluid, the non-wetting fluid is the green fluid. In here, the green fluid isn't connected as you go from the upstream side to the downstream side, so it physically can't flow. Remember, we're not really changing the saturation when we're flowing at this particular magnitude. All the red stuff is happy flowing in the red area. All the green stuff is happy flowing in the green area. We're not changing the boundaries between these two in any way. And so in this particular case, we'd get flow of the green fluid and the red fluid out because the rel perm curves are both greater than 0. In this case, we'd expect to get none of the green fluid out because there's no connection from the upstream side to the downstream side for green fluid to come in here and actually make its way across here and come out the other side. So I guess always try and link these in some way with a physical understanding of what's going on. So you'll make yourself invaluable to whoever your employer is, right? Okay. So as always, I'm speaking too much more than I should do to be able to make the points I want to. Let me roll through this. So this seems like a waste to me because it seems something that just doesn't lodge itself. But the point is, when you talk about relative permeabilities, we're talking about a core, and if we assume that the gradients are uniform in that core, we can calculate the amount that comes out of the downstream and equivalent actually goes in the upstream as a function of the pressure difference we have between the upstream and the downstream. So we can do the very simple calculation that we've just done, and that's probably enough for this class. But if we wanted to look at a system where, for instance, we have different saturations at different locations in different places, and I'm looking at what I have for this class. I thought I had some images that I had, and so if I put, yeah, okay, so this. I don't know whether that's better than this or, yeah, okay. Oops. So in other words, if you look at this behavior that we've talked about here, and you want to look at flow in the system, then, well, it's taking a long time to think. I don't know why it's taking so long to think. Is if you look at this, the saturation that you have here versus the saturation that you have here, they're different. And so if you wanted to look at flow through this system, then the behavior you have isn't just this uniform core, that you have a given saturation everywhere in the core, but it changes from location to location. And if you put a drill hole down in here to be able to suck out this free product which is sitting here, then the saturations in this particular case would change as a function of time as you invade it. So we need a more complicated way of solving a problem, one where the saturations may change as you go from location to location. And the way in which we do that is by using conservation. And if you think back to your fluids class, you may be frightened by this conservation expression, and you may not remember it. But we dealt with an expression which looked like this. This is a mass flow rate in some kind of control volume. This is, bless you, density of the fluid. This is the volume of the fluid, of the container. And this basically said that if you take a container, and our container is basically a little differential volume, and if you look at the mass that flows in from the upstream side, the mass rate of flow that goes in out of the downstream side, if these balance each other, then there's no net accumulation. And if the volume of this control volume doesn't change with time, then this term is zero, and we can differentiate this by parts. And if we differentiate by parts, we have something that looks like a volume times the change in density of the fluid with time plus mass flow rate in minus mass flow rate out. And this is a conservation equation. So it says that if the amount going into the system is greater than the amount going out of the system, then we have to have a net accumulation. If the volume of this control volume doesn't change with time, the only way we can do that is by changing the density of it, by making it more dense because we're cramming more stuff in because nothing else is going out. And that was basically what that expression is. And so you might have thought you'd never see that again, but this is kind of the basis of any groundwater flow problem. And it says that mass in minus mass flow out. So this is a volumetric flow rate or a velocity times a density. So volume, a velocity, this is a velocity times a density. And so you can imagine that the velocity times the density over a particular cross-sectional area, A, gives you a mass flow rate. So it's this term here. And this is a term which relates to the density change for a constant volume. And so although this control volume is constant, what could change if you have two fluids in it, you could get more water in, and that would push out more of the non-wetting fluid to be able to accommodate it. So the saturation of the water might increase, but the saturation of the non-wetting fluid in a complementary way would decrease without changing the volume of this control part. And so if you look at the volume of the fluid, which is in this case, it's going to be something like the total volume of this control volume, right? And what is the volume of water that's in there? Well, the total volume of this times the porosity is the volume of the voids. The total volume times the porosity times the saturation of that particular component would be the volume of the fluid. And the volume of the fluid multiplied by the density of the fluid would be the mass of the fluid. And so what this is saying is that the mass in minus mass out has to equal the mass rate of accumulation. So this is a mass of fluid, and this is the rate that it accumulates. So that's all I'm going to say about that. But it's the basic basis of any kind of multi-phase flow problem, is that if you can define this conservation of mass as a function of the porosity, the saturation, the density of the fluid, and the flow rate at which the fluid is going into the upstream portion or out of the downstream portion, this is Darcy's law, right? We know that we've written it as velocity is equal to relative permeability, permeability over viscosity times dP dx for a single phase, well actually no, for any phase. And so if we substitute this into this, we end up with a conservation equation. And I won't go through the derivation because it's not relevant to what we're doing here. We end up with a conservation equation for phase 1, let's say water. And what's happened is that we end up with a pressure of the fluid and a saturation of the fluid. You do the same conservation equation for the other fluid that you have, which is the non-wetting fluid, and you have a second equation. If you have a second equation, then you'd like to be able to solve it, but the problem is, to solve it, you have too many unknowns. You have a pressure in the water, you have a pressure in the oil, you have a saturation of the water, and you have a saturation of the oil. And so you have two equations you want to solve, but you have 4 unknowns, so you have to figure out what to do. And so for 4 unknowns, you need 4 equations, so you need to get 2 other equations. One is that you know that when you add the saturations together, they have to add to 1. And so you can intrinsically, for instance, you could write S2 and substitute into here as what? S2 is equal to 1 minus S1. So in other words, we don't have S2 anymore, we have S1, P1, and P2. And we have some way of being able to link these. And the way we link these is through the capillary pressure versus saturation curve, which is just this expression, this diagram that we've had here. So capillary pressure versus saturation. And so we have 4 equations, we have 4 unknowns, and we can solve it. And that's it. And so we won't do that, but if you wanted to, you could be able to solve it. Turns out you can solve these for relatively simple geometries. And so let's look at just one very straightforward example. And then I think that's where we'll leave it today. Yeah, I'll leave it today. And that is, it's called Buckley-Leverett curve. And the idea is basically this. Can I do this? So this is the geometry. So the idea is that you want to pump a fluid into this reservoir. This is your reservoir. Happens to be inclined. It doesn't matter that it's inclined. And what you're going to do is you're going to pump fluid along this reservoir. And if you look at the direction along this reservoir, this is what we'll call this uppercase X along the length of it. And so what you could think about it is in terms of the saturations of the fluid as you go along the length of this. And actually this graph here is the only graph that we need to do. And perhaps it's easier if I try... Can I do this? Will it do it? It does do it, but I didn't want to be on that page. Yeah, okay. That's exactly what I want to do. So this is the profile along the length of this. So this is our reservoir. So if you think about the reservoir here, we want to flow water in here, a wetting fluid. And if we do that, then we can look at the saturations along the length of this core. And the saturations are the saturation of water. So this is fully water saturated here. This is fully oil saturated, zero water saturated here. And so where we start with, in this particular case, is the initial saturation would be this point along here, right? So this is starting in an oil reservoir. You start in an oil reservoir. The amount of water in the oil reservoir maybe is 10%. The amount of oil in that reservoir is the remainder, which maybe is 90%, right? So that's the initial condition. So to be able to suck the oil out, you can't just suck it, you have to replace it by something else, so you force water in to be able to displace it. So we're forcing water in through this top region. So what do you expect to happen to the saturation as you force water in? Well, instead of the saturation being this horizontal line here, it's going to change at the inlet because all of a sudden you're going to pump water in. And the amount of water you can pump in now, the maximum amount is going to be this amount. And this is going to be the total amount of water minus the irreducible saturation of the non-wetting fluid, right? This is SNW0. So this height here is the amount of oil that we can't get out of the system and can never get out of the system. And so at this particular point here, right at the entry, we have 20% oil and 80% water. As you keep on pumping water into it, then instead of the profile looking like this, then after some period of time the profile will look like this first curve here. So if you like, you can think of this as a tongue of water, and so everything that's below this curve here, as I go horizontally as well here, this all is water underneath it. So 80% saturation here, 70, 60, 50, and back to the original 10% saturation of water as you get ahead. As you keep on pushing it, then all of a sudden, at some later stage, this would be the profile of saturation. And again, at this particular point here, this would be the amount of water. This would be the amount of oil. And it looks at the profile. And so it turns out that those four expressions that we developed, you can solve relatively straightforwardly to get an analytical solution to this problem, to be able to say something about the displacement process. And so in the cases where the saturation is changing, which clearly is changing, right? As you go from this point here to a place downstream, the saturation changes from 75% to 72% to 65% to 60% of water, etc., and the corresponding amount of NAPL. And so by solving those expressions, you can do something about solving that particular system of equations. And so you won't need to solve those in any way, shape, or form, but you should realize that all the stuff that we did in 303 in terms of conservation of mass was not all in vain. And actually, if you want, I'm sure you're chomping at the bit for this, but if you want to go and look at exactly how you move from this relationship for conservation of mass to get to the continuity equation or the governing equations for porous media flow, you might go to this YouTube site and look up lecture 8.2. Oh, I guess I can't. 8.2 on 303. I can't imagine you'll do that, but if you do want to do that, it's there. So, and I'm not going to show it here because I'm not online. So there's some advantage of having these record components. It's about the latter portion of the class. So the final thing before we pack up, which I haven't dealt with, the other thing which is important when you're looking at recovery of components from porous media, and you will do an assignment on this, as I say, I think it might be assignment number 4, is this idea of what happens if you have, as a function of this geometry, and I realize I can't actually write on these. So what happens if you looked at this being a plug of NAPL, which is present at some saturation, and you're looking at flowing water across the length of this? So although I can't write on this, the kind of core would be flowing from this upstream side across here. So if you think of this as a piece of core that you're flowing water through, with this NAPL chimney taking up the middle part of that core, then it's a little bit like this geometry here, where you have a core that has a NAPL plug which is present in the core, in the center part of it, at some saturation, saying the non-wetting saturation is 20%. Then clearly you can get water going across here, and what it will do is it will dissolve material and take it out the other side. So this is basically a pump and treat system. You have it sitting here at some saturation. You should be able to calculate what the relative permeability would be at this particular saturation. If you know what the relative permeability is at that saturation, then you'd know exactly what the actual permeability was. And if you know that permeability, you'd know what the volumetric flow rate is because it is given by this. So if you knew what the gradient across this was, you knew what the permeability of this soil was, if you knew what the relative permeability is as a function of saturation from a curve like this, then all of a sudden you can calculate the flow rate. I know that's quarter to. And if you know the flow rate, you can calculate the mass rate at which you remove your contaminant is going to be the volumetric flow rate times the solubility. Actually, it's going to be that. It's the mass flow rate multiplied by the solubility. So I'm meeting with someone in 15 minutes. And so, if you know the rate at which you're removing fluid from here, you'll know the rate at which this saturation will decrease. And if you know the rate at which this saturation decreases, you know the rate at which you'll move down this curve here to be able to look at the relative saturation. Actually, it's not here, right? It's going to be here. So this is 20% saturation of the NAPL, 80% saturation of water, and you'll move across in this point to get 100% saturated water. So you should be able to calculate the evolution of that. All right. Just too much enthusiasm, I know. Assignments due Thursday. I don't think anything other than that. I'm around Thursday. Taha's available to help as well if you need it. And we'll talk next time about some applications, if you like, pragmatic applications of these next time, because we've finished with the background calculations. Okay? Thank you.